So now we turn to groups, which we're going to view as metric spaces, actually more precisely associate metric spaces to groups in a not quite canonical way, which lets us study geometric group theory. That is, they become geometric objects in this. Okay, so suppose now here G is a group and S is a finite generating set. So this means that we have assumed that our group is finitely generated. Yeah, so it being a finite generating set means that each G in G can be written as a product of the generators and their inverses. So it can be written as G equals S1 plus minus 1, etc. So Sn plus minus 1, where S1 and Sn are generators. Okay, so I'm not taking symmetric generating sets. Sometimes by convention we assume that the inverses are also in S, and so then you don't need to put plus minus 1 here. Okay, and so each element can be written in this way, what is called a word metric. Well, so far we are just looking at the corresponding norm. Is the following. So definition of the norm of G is the smallest n such that there exist S1 Sn in S, and let me be precise, epsilon 1 epsilon n in minus 1 1, such that G is S1 to the epsilon 1, S2 to the epsilon 2, Sn to the epsilon n. Note, I'm not saying this is the shortest expression. I mean, it is a shortest expression. So it's the smallest n greater than or equal to 0, such that we can find appropriate generators. By the way, these can repeat. Si may not be distinct, and usually are not. In fact, S is a finite set, and n may be much larger than the cardinality of S. So by pigeonhole principle, they will repeat in that case. So usually they don't repeat, and usually they do repeat. So the smallest n for which you can find such an expression is called the norm of G. It's telling you the length of G. Some sense. So let me have just a convention, which is a standard one. E is the empty product, or I should put it the other way around. The empty product is the identity. In the case of any associative product, we will want to make these conventions. Okay, so of course norm E 0. Let's look at some properties of this. So properties of this norm function. Okay, sometimes we'll put norm S to emphasize it's dependent on S. Well, first of all, norm G is non-negative, with norm G equals 0 means that G is an empty product. And this happens for the identity and only for the identity, if and only if G equals E. And B, second property is that norm of G times H equals, need not equal, it's less than or equal to norm G plus norm H. Now this is a simple fact, but just to get used to the definitions, let me give a sketch of a proof. As, let's say norm G equals n and norm H equals m, then there exist S1 Sn in S and T1 Tm in again S, such that G can be written as S1 where plus minus 1, Sn plus minus 1. I won't put explicit notation for the sign, and H can be written as T1 plus minus 1, Tm plus minus 1. So this means you just multiply them together. And what you get is G1 S1 plus minus 1 Sn plus minus 1 T1 plus minus 1 Tm plus minus 1. What does this say? That is GH can be written as a product of M plus N generators and inverses of generators. Inverses of generators, what is the consequence of this? Remember what is the norm? Okay, so the norm is the smallest way in which you can write it as a product. Now you can write it with N plus M, and so you can perhaps write it with even fewer or perhaps not, but whichever way it is, norm of G plus H is at most N plus M, which is the sum of the norms. Okay, so we have seen, well, these are the usual norm properties. We also see another simple fact, which is norm G is less than or equal to 1 if G belongs to S is a generator. This by definition, it can be written as one letter. Oh, I forgot to add, let me call this D. C is the more fundamental property. It's that norm G inverse equals norm G. So I'll call this an exercise. You should do this exercise to get used to what the norm is. If I invert it, well, then I have the same norm. And so A, B, C are the main norm properties, but we have an additional property, norm G is less than or equal to 1 if G is in S. By the way, it seemed as if it's equal to 1, but I haven't ruled out identity being just included in S. Okay, but this is nicer to way to say it for various reasons. Namely, we have the following exercise, which says norm G is maximal. Okay, I'll be very precise. So norm is maximal. Namely, if nu mapping G to R satisfies A to D, A, B, C, D, so nu is another norm and is less than or equal to 1 on the generators, then nu of G is less than or equal to norm G for all G. Such characterizations of metrics are very nice. You say it's the largest metric or smallest metric, usually the largest metric, such that some inequalities hold and some conditions hold. Okay, so this will also be useful in various contexts. So now from the norm we have a metric, the word metric. Well, it's the way you do make metrics. So definition, D, let me write subscript S, which is the set G comma H is norm of G H inverse. We could put the inverse in the other place, you'll get the, well, it might make a difference, but so you get, so exercise. This is a metric. Okay. So this satisfies the triangle inequality because of the corresponding property for norms. Namely, norm of G1, G2 is less than or equal to norm G1 plus norm G2. And the other properties again come from the A and B, A and C, I should say, of the other metric. The symmetry comes from the fact that norm of inverse is the norm. Okay, so exercise, this is a metric. What is the weakness of this metric? So it looks as if we have converted groups into geometric objects, so this depends on S. And one of the major steps in geometric group theory is to see how to address this weakness, that is, understand the dependence on S. Now let's just take an example, both to understand dependence on S and the word metric itself. Let's take G equals Z squared. So if I take S equals 1, 0, 0, 1, okay, the norm of 3, 2, the vector 3, 2, with respect to S. Well, I'll have 3 copies here and 2 copies here of the generator, and there's really no choice, I mean, other than adding excess stuff. So this will be 5. On the other hand, if I took S equals 1, 1 and let's say 0, 1, the norm of 3, 2, S prime is going to be just this is going to be 3. Okay. Oh, maybe I should take 1, 0 here. Perhaps it's true the other way too, because this is going to be 2 times 1, 0 plus 1, 1 plus 1, 0. Okay. So now with respect to S prime is this. So as you see, it depends on the norm. Okay. So this is what we'll address later, but for now, let's look at another construction of a metric space associated to a group. So we take a Cayley graph. Well, this is gamma of the group, but it's really gamma of G comma S. Okay, so this is a graph. And to tell you a graph, I have to say what vertices are. So vertices are just elements of G. What about edges? Edges are, they join, which vertices they join? G to GS for G in G, S in S. Okay. And here we'll be taking metrics along graphs, that is, we measure paths along graphs. So we take an example, we'll take our usual one, Z squared, with S equals, so G is a Z squared. Let's just take 1, 0, 0, 1. Then you get something like the unit lattice. In fact, you have the unit lattice as the G. Let's take a few points in it. And edges join a vertex to something that's connected by a generator. So these are the edges here. In fact, you see, you'll get just the vertical grid right through to this. But I should emphasize this is with what is called a Manhattan norm, because it may sit in R squared, but we are measuring distances along the graph. So if I want to go from here to here, well, I have to go along the graph. Perhaps I chose this path. There are lots of paths which are minimum length, but we don't cut across the diagonal. Okay, so this is called Manhattan norm, because the streets of Manhattan, at least if you don't go too far south, look like this. Okay, so this is an example. So here's an exercise. Well, G itself is a subset of this. G includes in gamma of G is an isometric embedding. That is, the distances are all preserved, but it's not onto. If we take, well, what metrics are we taking? So here we are taking word metric with respect to S, and here we are taking the, for any fixed generating set, we are taking the Cayley graph with respect to S, and we are taking the word metric with respect to the same S. So long as you do that, you have the distance from the word metric and distance from the Cayley graph are the same. Okay, so just a couple of remarks to end. So we have associated two metric spaces. The word metric is nicer in the sense that a set is just a group. We have put a distance on it. We haven't added more to it. So it's cleaner in a way. But the Cayley graph has a major advantage. It's a geodesic metric space. And this isometric embedding will let us pass from one to the other. Okay, and these, so we will be using both of these as metric representatives for a group, but with the caveat that these do depend on the generating set S. In both cases, there's no truly canonical construction, so our next goal will be to understand this dependence.